Welcome to our video tutorial here on identifying the equation of a graph of a logarithmic function. We are going to look at two such examples. Here's the first. So my advice for the best thing to do initially is look at which log we want it written in terms of and sketch that original graph slash parent function. It just helps you have an idea of how the log is supposed to look in its normal positioning. From there, we are going to have to identify what transformations the graph underwent. From a reflection standpoint, it reflected across the y-axis on this problem, so we'll note that it was reflected across the y. It was not reflected across the x, but maybe there was a vertical stretch. So let's analyze. In the original graph, vertically speaking, between our two key points, it was a distance of 1. In this new graph, vertically speaking, between our two key points, it was a distance of 2. So in this problem, we are going to have a vertical stretch of 2. Next, we have no reflection across the x. We have our vertical stretch. We have a reflection across the y. How about, let's look for a horizontal stretch. Is there a horizontal stretch on this graph? Over here, horizontally it goes 6. Over here, horizontally it goes 6. We don't have any horizontal stretch. The other question could be left, right, up, down. So originally, the graph had its vertical asymptote at x equals 0. Now it's at x equals 3. That means we moved it to the right 3. And the other thing that we need to consider is any up-down movement. Well, we had a vertical stretch of 2. This point, a vertical stretch does not affect, so it appears that we moved it up 1 at the end. So when we're writing out the equation of our new graph, if this is the graph of y equals f of x, we would have f of x is equal to 2 times the log base 7 of the opposite, be careful that's the reflect across y, of x minus 3, that entire quantity, plus 1. There would be the equation of the graph that's pictured. That would be equivalent to writing 2 log base 7 of negative x plus 3, all in parentheses, plus 1. But be careful how you handle distributing that negative sign and working it out accordingly. Here is our second and final example of identifying the equation of a logarithmic graph. Notice what we want it in terms of is the natural log of x. So really quickly, we're just going to get that basic graph on the screen. It has two key points. One is always at 1, 0. The other point is always at the base of our log. In this case, it's e, 1. Okay, so this graph did not get reflected across the y-axis, but it did get reflected across the x-axis, so we'll start with that. Vertically speaking, the original graph vertically goes 1 between those 2 points. On this graph, vertically speaking, it has 3 as the difference between the 2 points. So we do have a vertical stretch of 3. Horizontally, between these 2 points would be 2e minus e plus 1. When we distribute the negative and simplify, that would be e minus 1. Over here, it's likewise e minus 1. So we did not have a horizontal stretch come into play with this graph. Next, we want to consider left, right, up, down. Notice over here the vertical asymptote's at x equals 0. Over here the asymptote's at x equals e. So we moved it to the right e. And last but not least, this point at 1, 0 is not impacted by a reflection across the x-axis, nor is it impacted by a vertical stretch of 3 for its y-coordinate. So it went from 0, it ended up at e, that means it went up e for the graph. So if this is the graph of y equals f of x, our equation would be f of x is equal to negative 3, that's the reflect across the x in a vertical stretch of 3, times the natural log of x minus e, because we're moving it to the right e, and then plus e, because we're moving it up e. That would be our final equation. Let me fix that up just a little bit because that doesn't look necessarily like x minus e. There, that looks better. That would be the equation. And while we're at it, remember there is not a formula or a log property for the difference inside of a log. So that can't be simplified at all. That is our final